Hello, my name is Michael Nurnberg, and today I'll be presenting DP3. So, we decided to make an automatic t-shirt folder. We intended to target the college students and secondly, the elderly. We just wanted a more efficient way to fold shirts. Here we have the use case, and essentially what we found from this is many college students, they have homework, they have activities after school, and laundry is not the number one priority for most college students. So essentially, we found that if we had a device to help aid folding laundry, more college students would then fold their laundry and have a more neater room. After interviewing a few customers, we found that the efficiency for folding the laundry is the most prioritized aspect of the product. So in our design, we tended to lean towards the fastest way to fold a shirt. So here are our concept generations. Each one of the teammates made 2 concept generations, and each one of the drawings had different aspects that set them aside from others. So I chose servo, Justin made more of a cable system, Colin used more like pneumatics, and then Charlie had the gear and servo linkage system that we ended up using in the end. So how we selected which design we ended up doing, we made a concept scoring matrix, and as you can see here, we had different selection criteria that had different weights to it. So first we had easy operation, and then we had the lightweight, like so the weight of the actual product, quick folding, small profile, low power consumption, how quiet it is, and the affordability of it. Obviously, the quick folding had the highest weight to it just because that's the biggest design implementation we're supposed to have. So an important aspect to look into when designing any product is looking at already present patents. So we did some research. We found that there's 5 different patents that had similar designs to ours, not quite the same. And what really set ours aside is our specific design, like to how to mount the linkage. Many of these patents did have very similar designs, but we do not think we impeded on any of these already present patents. So if the product were to go in production, we wouldn't face any legal issues or anything like that. Okay, so with any product that goes into the market, FMEA has to go into consideration, which is the failure mode effects of engineering analysis. And essentially, we just break down the product and see where the product could fail and how it could fail. So basically, we took into account the motor could be too powerful and actually cause the lever arm to disconnect and fly away. So to fix that, or to ensure that wouldn't happen, we could use Loctite on the screws and ensure they won't back out. Another mode of failure we thought could happen is the folding flaps breaking. So to fix that, we could reinforce the backing of the folding flaps so they're not as floppy and will not break. Another thing we took into account was the actual flaps breaking at the hinge. So we ended up using larger hinges than originally used in our original concept generation. So that will be reinforced and make it better for the actual folding process. And then lastly, the linkage could possibly break. So we actually end up changing our design to make it have a thicker hinge or linkage, so it will not break as easily as our original design. So we took into consideration the assembly time and manufacturing costs. So with anything, the first product or the first manufacturing process is going to take the longest, and we applied a learning curve of 95%. So each product is going to be taking less time than the one before that. And in total, we calculated that the average cost per tidy is $14. And in total, for the break even, it's going to be around $364. Here's our bill of materials, which is all the product or all the products in our design. It actually came out to $170, which is not our targeted cost. We want it to be pretty affordable for the college student. We aimed for around $60. So if we were to actually go in production, it could be a lot cheaper if we bought a lot of the parts in bulk and made a lot of the parts in-house. So we think we could still average around $60 if we were to go into production. So $170 is pretty steep for a prototype, but it will be dropped down if we were to go in production. So we actually did get some quotes from Protolabs to see how much it would cost to 3D print through them. It is pretty hefty at $1,089 for the 3D printed part. That could be brought down just if you bought more units. And we also got another quote for injection molding, which is even more pricey because they have to actually make a mold for our product. So both of these could be brought down in price if you buy it in bulk, but realistically we could do both these parts in-house. So here is our CAD model drawings. As you can see here, we have a linkage connected to the servo, and then we have another linkage connected to the folding flap, and together that will lift up the flaps on either side of the tie-D. So essentially, there's the same design on each flap, and each one of them are controlled by a servo, which is connected to our Arduino. And then for our power source, we have the external outlet, or external cord that plugs into the outlet and then into the Arduino. And then we have a button to actually power the system on the outside of the tie-D. Here is our final design. Essentially, it was made out of wood just because cheapest thing we could find. Each of these top panels were made out of Luan, which is a lightweight material. Made it so it was a lightweight, and then it was easy to have the servos move. Each one of the pieces here were cut using a table saw, and then the box itself was made using a nail gun to fasten it. And then the servo linkages here were 3D printed and fastened down with some screws and pop rivets. So with any prototype, there will be some imperfections in it. It's the first design. So as you can see here, in the OSB wood, you can see some splintering. Not the most ideal thing, but in the future, the product could be made out of different materials, like acrylic or different pieces of wood. Essentially, we just use OSB because it's something that's laying around, something easy to build out of. Also, you can see here that nails are popping out from the nail gun. Like I said, just imperfections. So the design process could be refined and be better for the market when you actually were to sell a product. That was it. Thank you for watching, and yeah.